video, I will give you an introduction to binary search tree. This is a binary tree because each node is having a maximum of 2 children. Let us see the definition of binary search tree. Is it binary tree? Of course, it is also called a binary sorted tree where each node is having these properties. The first one is that each node n has a key. This key is a unique value in each node in a binary tree. In some resources, this key is represented as a value in the node. Since a value may be a data or a key or an address or something else, then it may create a confusion to the learner. So that is why I always mention key here, which is definitely a value, but not the data inside each node, right? And the second property is that the key of each node n is having a value that is greater than the keys of all nodes in the left subtree with regard to n and is less than the keys of all the nodes on the right subtree of that n. That means on the left hand side, with regard to A, you see here, this is the left subtree when the root is A, and the root A is having key 44. You notice here that B is having 39, C is having 14, D 42, and E 20. So these keys of all the nodes on the left subtree with regard to A is having lesser values than 44. On the right hand side, you see all the keys are having a value greater than 44, right? Similarly, with respect to the root B, the left subtree is having 2 nodes, that is C and E, and both of them are having keys less than 39. And on the right hand side of B, only one node is there with a key 42, which is greater than 39. Similarly, here also 55 and 60 both are less than 67, and the right subtree is having 89, which is greater than 67. So when these properties are followed by a binary tree, then we call that binary tree a binary search tree. There is an analogous definition also that allows equal values of keys between the key of n and the keys of the nodes in the right subtree of n. The meaning is that if we consider the whole tree, then the root here is 44. This yellow shaded definition says that if 67 is here on the right hand side, so the root may have 67. Or if you consider this subtree where root is f with 67 as a key, then on the right hand side there may appear some node like this where, say, the name of the root is m and it may have 67 here. That means this shaded definition is allowing you duplicate keys in a binary tree. Of course, the duplicate will always be there on the right hand side if it is allowed. Duplicate key is not allowed on the left subtree of any node n. Just keep in mind this one, right? Now, there is an observation. We have learned in-order traversal on a binary tree, in which the algorithm goes like this. The step 1, you move towards the leftmost path of the current node, and when you cannot move further on the leftmost path, you go to step 2 and process that node where you are standing. After processing, you move to step 3 and move to the root of the right subtree. And from there, you start moving towards the leftmost path by following step 1. So this was our in-order traversal, right? Now this in-order traversal over a BST, that is binary search tree, guarantees that you get the keys in a sorted and ascending order. That means if you perform an in-order traversal over a binary search tree, then the keys you visit will be in an ascending sorted order. Let us check in-order traversal over this binary search tree. First, you start from here and you move towards the leftmost path and you stand at B. There is another left path, then you move to C, and from C you cannot move forward, right? Because there is no left child from C. So you stop here and go to step 2 and process the current node. So if you process the current node, say our processing is just printing the key, okay? So you print the key and the 14 will be printed, right? Now you are standing here. Step 3 says that you move to the root of the right subtree. Then you move to E. That means you are standing here. Now when you are here, then you go for the step 1, and the step 1 asks you to move towards the leftmost path as long as you can. Now there is no left child from E. So you stay over there and move to step 2 and process the node. So you print 20. Now you notice here that C and E belongs to the left subtree of B. That means the whole left subtree with regard to the node B has been processed. Since this has been processed, then we go for processing the root, that is a B, which is 39. So we get 39 over here. After that, we move to the right subtree, which is at D. From there, we try to traverse the whole left subtree, but there is no left subtree. So we process the root, that is 42. Then we try to move towards the right child, but there is no right child. So in this situation, this whole subtree, which is the left subtree with regard to 44, has been traversed. So we move to process the root A with the key 44. So we get a 44 over here. Then we move to the right child at F with the key 67. And from there, we start to move towards the leftmost path and we stand at G now, which is having the key 55. From there, we cannot move further towards the left. So we process G, which is 55. So 55 is here. After this, we move to the right child, which is I with the value 60. From there, we start to move towards the leftmost path, but there is no left child. So we process I with the value 60. At this moment, this subtree, which is the left subtree of F, has been traversed. So we move to process F, which is 67. After this, we move to H, and from there we try to move towards the leftmost path, but there is no left child. That is why this H will be processed and we get 89. After processing H, we try to move to the right child, but there is no right child, so our traversal is over. So you see that you have got assorted keys from this BST when you perform in-order traversal. Of course, this will not happen if you perform pre-order or post-order traversal. Now we talk about the necessity of this binary search tree. What is the use actually? The main use of this binary search tree is to search some item. This tree structure will help you to search item in an efficient way. Based on this searching, you can get a lot of applications. It is easier to handle a binary search tree. For example, if you want to add an element, you take that element inside a node, find the location where it is most suitable, and then just attach the new node to an existing node. For example, if you want to go for inserting 13, then you say that 13 is less than 44. So come over here, you see 39. So still 13 is less than 39. So come on the left hand side, there is a node C with 14. So you again come on the left hand side and you find null over here. So you can attach this new node over here. maybe the name of the new node is X. Compared to array, handling a BST is much easier. If you want to insert values, if you want to delete values, if you want to relocate any data or any node from one location to another, it is easier in BST than an array. Now, here is an advantage, and most important one is that in a BST, if you go for querying some data which is not present inside this BST, then it will take you to that location which is very near to the queried value. For example, if you want to go for say 57, now 57 is not there in this BST, right? Now if you try to find out where is 57, you will definitely visit the root first, that is 44. So your queried value is 57, which is greater than 44. So you move to the right subtree and you see that the right child is 67, which is the root of the right subtree. Now visiting 67, you see that the 57 is less than 67. So you move to the leftmost spot, that is the left child, and you visit G, which is 55. I have to move towards the right child, and you find that 60 is there. So if 60 is there, then you cannot move further because there is no right child or there is no left child. So 60 is the nearest data to 57. In the next video, we'll discuss about the searching technique in a binary search tree.